there are a lot of things in real life that we say have exponential growth, that are growing very rapidly, very quickly. Sometimes we look at populations that way. We're going to look at money and things like compound interest. The sound, there's loud sounds and quiet sounds, and their difference in sound is so much that they put it on an exponential scale. Earthquakes, the measuring earthquakes from just a little bit to a huge amount increase so much, so quickly, it's on an exponential scale. We would have seen it last couple of years with diseases, how fast they can spread. An example of COVID and Ebola, if things don't get under control, it can get really bad really quickly. Okay? And then there's also things that decay. There's half-life of radioactive substances. When you take Tylenol, the drug in your body gets reduced. So we're going to look at some of these applications. And the first one, which we looked at a little bit already, we'll do some more, is compound interest. Again, in this unit, they can ask you any word problem with any formula that's out there, even if you haven't seen it. But they will always give you the formula and what things stand for in the question. So if you get a compound interest question, I'll give you the formula, and I'll give you what each of the things stand for. A is the final amount, P is the principal, N is the number of times compounded per year, R is the rate, and T is the time in years. And so what I want you to do with this first question is just plug things into the formula in the right spot. What is the final value after 10 years of $500 invested at a rate of 2.25% compounded month? And let's check, did you plug everything into the right spots? And then this one's just a matter of typing that into your calculator. So I would also say right now, take out your calculator. See if you can get $626.03. Want to check if you can put the values in, type them into your calculator. Oh, extra notes, what we're doing right now. And then check how you did. So these first two are really easy. Once you plug things in, you just type the whole thing into your calculator and you get the value. Again, I want you to look at that next question while we're waiting here and see if you can just plug the things into the formula correctly. Did you plug it in correctly? If it's going to double, it's going to go from $30 to $60. But now what's different in this question, we can't just plug this into our calculator to solve because we want to solve for t. Okay? Now, a strategy we talked about the other day is if you're solving for t and you can't get the powers the same as a calculator question, you're going to use logs. But if you're going to use logs, usually we try to get the power by itself first. So if I divide both sides by 30, I will get 2 equals, and then we've got the power by itself. This allows us to take the log of both sides, which would mean that that exponent would come out in front, because that exponent is to the entire power. Divide by the 12 and the log 1 plus 0.07 over 12 to get the t by itself. And we get an answer 9.93 years. Now, something fascinating is going to happen in this question. The first fascinating thing that happens in this question is that if you had to redo it, and instead of asking how long would it take $30 to double, you ask yourself how long it would take for $1,000 to double. Can you see if I asked how long it took for 1,000, I put 1,000 here and 2,000 here. But when I divide by 1,000, wouldn't I get the exact same equation? It would be 2 equals. No matter what amount of money I put in, if you get 7%, which is a little high for right now, but not crazy. Like there's places giving out 5%, which is close. If you get 7%, it's going to double in about 10 years. And it's going to double in 10 years if you do $30 to $60, or $1,000 to $2,000. Or if you happen to have $5 million, it would double if you had $5 million, right, and you got 7%, it would be $10 million in 10 years. I'm trying so hard, I haven't found it yet, someone I'm like, could you just give me $5 million for 10 years? I'll give it back. Wouldn't that be nice? Because it would double, and then when I give them their $5 million back, I've got $5 million as well. Like, this is a good deal. But I haven't found anyone working on it. But nobody's just willing to give me $5 million right now. Something also very cool with interest rates is something called the rule of 70, or sometimes it's called the rule of 72. And the rule of 70 and the rule of 72 is so simple, it feels like it shouldn't work, but it works. The rule of 70 or 72 says you take 70 or you take 72, you divide by the interest rate that you're getting, and it will give you an approximation for how long it will take for investment to double. So we just figured out in this previous question that at 7%, it takes 9.93 years to double. The rule of 70 would say all you need to do is plug in 7 for I. And the reason there's a rule of 70 and 72 is just whatever mental math is easier. So I would put the 7 into this one, because 70 divided by 7 is 10. And that's easy mental math. And it tells me it would take about 10 years to double. If you got 8% interest, I would use this one, because 72 divides nicely by 8. And if you got 8% interest, it would only take 9 years to double. 5% interest, I'd probably use this one, because it divides nicely by 5. And 70 divided by 5 is 14. So if you got 5% interest, it would take that $5 million 14 years to double. You'd have to tell your friend, hey, I just need to hold on to this for a little bit longer, and then I'll give it back to you. So the rule of 70 and rule of 72 is a very quick way to estimate how long something's going to take to double if it's compound interest. And look how much less work that is than this, right? It's a very quick way to find out how long it takes to double. Same thing would happen if you invested a dime, 7% interest. 10 years later, you'd go to your bank account and you'd have 20 cents. Now that wouldn't be it's not nearly as exciting. I found people who have been willing to donate a dime to me to do this investment. The 5 million, not yet. The 10 cents are like, sure. Four years ago, Andrew invested in an RRSP. Interest rate was 5% compounded quarterly. If the RRSP is now worth $2,500, how much did Andrew initially invest? Again, what I want you to practice is see if you can take the formula, plug everything into the right spot. And you can check, did you plug everything in the right spot? And now we're not solving for an exponent, so you wouldn't need logs at all. You just need to divide to get p by itself. And Andrew invested $2,049.37. Okay. For this next example, I'm going to get you to write down the answer. 30.66. And I'll leave that one for you to try on your own as homework for at home. But we are going to do this one where it says, calculate the time it would take for an investment to triple if it's compounded monthly at 5%. And again, I'd like you to fill in the formula first on your own. Now, the tricky part in this one is it doesn't tell you how much, right? So you actually are allowed to make up a value. You could pick $1 and it could triple to 3. You could put $2 and it triples to 6. no matter what value you pick, you should just have 3 after you simplify. If you pick 10 and 30, when you divide both sides by 10, you would just get 3 equals. And now we're solving for the exponent. So we take the log of both sides, use your log laws to get t by itself. And if I had that friend borrow me $5 million, we figured out that that $5 million would double using the rule of 70 in about 14 years. But if he would let me keep it to 22 years, it would triple. That's almost unfair. Because if someone has lots of money, they can just invest that money, not do anything, and in 22 years it would be tripled. And in 22 years, if I tripled $5 million to $15 million, 10 mil, would I quit teaching? If instead of teaching for my salary, I could just do nothing and get about 500 million a year, I don't know, or 500,000 a year? Probably. So it's a little unfair because if you have money, then your ability to get more money increases. And it's very powerful, right? And for someone like you, just about out of high school and starting your work careers, this can be very powerful for your whole life, of where you're going to get to, how you can use the money that you have to double, to triple, to help you out. Next, we look at continuous growth. And the number E appears. If you took the compound interest formula, which pays interest on certain compounding periods. So if you invested and something was compounded monthly, like your bank account, every month they pay you interest. And they take what your interest would be for the whole year and divide it by 12 and give you 1/12 every month. Now, if that compound interest was paid daily, then they would pay you every day a little bit. But it would be pretty small because they would take what you would get in the whole year and divide it by 365 and give you that amount every day. But every day you would get a little bit, and the next time you would earn a little bit on that little bit. So the more times things are compounded, the faster it will grow. And eventually, if it was compounded continuously, like your bank account was just constantly growing, but just by billionths of a penny. So very little, but tiny little bits would be added on all the time. The compound interest formula turns into what I like to call the PERT formula, the continuous growth formula. And we use continuous growth, and again, in a question, I will always give you the formula. If you need the continuous growth formula, it will be in the question. In some of your homework, it's not, because the textbook says, well, it has the formula earlier, so you might have to find some of these questions. So what we're going to do here is we're going to look at, if you had $2,000 and you got 5.5% interest for 10 years, what would it be equal to? And we're going to look at compounded quarterly first. So quarterly would use the old formula, the first formula that we did. And not bad. Your $2,000 went up to $3,453. You made like almost $1,500 in interest doing nothing. Always exciting. You know what's not exciting? Doing nothing and losing money. That is not exciting, right? But that's what basically can happen in a stock market. you invest stuff into the stock market, it can either make you money doing nothing, or sometimes you lose money doing nothing, right? And be like, oh, I would have much rather gone to a concert and lost my money and enjoyed the experience rather than have it in the stock market and lose the money and not having any experience whatsoever. Now, the expectation, if it's compounded quarterly, which is only 4 times a year, they're only paying you interest 4 times a year. They're paying you interest all the time. This number is going to be bigger. I want you to think how much bigger you think it's going to be. Lots bigger, a little bit bigger, okay? Be prepared to be disciplined. It's like $12 more. Your brain should have thought lots more, right? Compounded continuously actually doesn't make a huge difference. In fact, what I always tell my students is that whenever you get a loan or when you get a mortgage, the biggest thing that's going to affect how much money you either make with interest rates or how much money you have to pay when you have a loan is the actual interest rate. And we're going to do some examples with that. But if you're going to borrow money to get a house, if you spend 8 hours and save yourself only 0.1% interest, it'll be the best 8 hours you've spent in a long time. Interest rate makes a huge difference. And we're going to see that in some of our examples. And if you can use this in the rest of your life, you can probably save yourself, I would say, compared to the average person that doesn't look at the math at all, I would say that I would have saved probably $50,000 to $100,000 already in my lifetime knowing how interest rates work and being aware of that. It is huge. So we're going to see what that looks like in some examples moving forward as well. But we'll finish these notes first. An investment of $200 is compound continuously, so we're using the PERT formula. We plug everything in. And with the PERT formula, since the base of the power is e, we're going to use natural logarithms. And once again, just like before, here's my power. So before I take the natural log of both sides, it saves me time if I can get that power by itself. So this one, it's easy. I can divide both sides by 200. And it's not wrong to take the log of both sides. But because the base is e, I'm going to take the natural log of both sides. All your log laws are exactly the same. Still can bring that exponent out in front. But then the ln e part is equal to 1. Because it's really asking, right? It's asking this over here. If I write it as a log, with a base of e, it's saying e to what exponent would be e? And the answer to that is 1. So then you would just need to divide both sides by 3 to get your answer. So once you've got this one down, I want you to look at the next one. Also, using the PERT formula, can you write everything into the formula in the right spots? All right, let's do a check. Did you plug it into the right spots? And then again, get the power by itself. I would use natural logarithms. Now these first examples that we've been doing with money, there's no bank that either charges interest continuously or pays out interest continuously. Because it's just too complicated to be like calculating in the moment what it would be. Most banks will give you interest monthly and charge you interest monthly. So the most common period is 12 times a year. They wouldn't do it daily, and we saw that even when you increase the amount of compounding period, it doesn't make a huge difference. So if all of a sudden a bank started charging you interest daily, you'd be like, I'm moving to a different bank. And the amount of money, little amount of money that they would make by doing that, and the amount of customers they would lose, probably wouldn't be worth it. So most things are done monthly. More common though, for continuous growth and the PERT formula is using the PERT formula for populations. Because we can either be really morbid in class right now, or really, happy. During class right now, all over the world, there's people that are dying. Someone probably just died in the sentence I just said. That's terrible. But at the same time, babies are being born. So we can be morbid and sad about people dying in the moment, or we can be happy and thinking about, oh, babies are being born. The same thing. Since class started, all around the world, babies popping. Okay? And so once population gets really, really big, we start to imagine it sort of being a continuous thing. Population is slowly increasing right now. People are dying, people are being born, but right now, more people are being born than people are dying, so our population is going up. So we can use this as a model, and it says, the population of Vancouver in 1981 was 1.38 million, and it has been growing continuously at an average rate of 1.7%. So that's going to be our R value. Change it to a decimal. The rate is 0.17. If we're predicting the population in Vancouver in 2011, that would be 30 years later, and we get 2.3 million. And as a population planner, was that too fast? Is someone not done? Everybody good? Gone? Almost? Okay. And as a population planner, if you're a city planner, you've got to be like, well, what's my city going to look like in 10 years? And if we don't do anything about that, you're going to run into problems in your city. You're going to have too many people. We need a better transit system. We need a better subway system. Should Winnipeg have a subway? What's it going to look like? So then the question is, well, we'll run into problems in Vancouver when we reach 6 million people. When is that going to happen? So again, plug it into this PERT formula, and I changed 6 million to 6 and 1.38 million to 1.38. And then we're solving for t, so again, I get my power by itself, use my natural logarithms, which would allow that exponent to come out in front, and of course the natural log of e is 1. Now, if you forget that the natural log of e is 1 and still divide by it,
Get a chance to try it out a little bit. I just want to see how you did.
all right, sounds good.
Yeah, it's pretty interesting. I found a couple, I had a different way of doing a couple of those. Yours was a little bit shorter, I think.
Okay.
I like seeing that.
I tried to find some even shorter videos on So according to this plan, Vancouver's going to reach 6 million people in 2067. What kind of problems would they have if there's 6,000 people in just Vancouver, not the greater Vancouver area? It's probably already has a population that big. And we can use continuous growth for animal populations as well. Now this will be the most difficult question that we have with the PERT formula. The reason this one is a little bit more difficult, because it says when the population of a herd of gophers was first studied, it was 15,000. 6 years later, the population was 18,000. If the population grows continuously, how long would it take to triple? And off to the side here, I was like, okay, I'll take 15,000, I'll triple it, but the problem is I don't know t, and I also don't know the rate. So this question's a little bit harder because we first have to find the rate. And we can do that because we're told enough information to plug into the PERT formula, so the only thing we don't know is r. Because we're told that in 6 years it went from 15,000 to 18,000. So we can plug in the 18,000, plug in the 15,000, plug in the 6. Again, get the power by itself. You'll get 18 over 15 when you divide both sides by 15,000. Again, the base is e, so I'll use natural logs. And I can solve for r. And then once we have r, and the reason I have the dot, dot, dot listed there is that you'll want to keep all the decimal places. Rounding early, especially in an exponential question, can have a huge change in your results. So if you're using a calculator, you can store that value or keep all of its decimals, because now we can plug in the r value. And again, students will ask, should I put the 15,000 here or the 18,000 for tripling? It doesn't matter. Because when you divide and get the power by itself, you will always get 3 when it's tripling. Okay? But that can be a place where you get stuck and feel like, what should I do? I don't know what I should do. I should just stop. No, it doesn't matter whether you use the 15,000 or the 18,000. Again, when I plugged in the R, I added the dot, dot, dot to say that I kept using all of my decimal places. And when I get t by itself and actually calculate it, it comes out to 36.15 years. Now, in this question, there was an error, an English error. So I'm switching you to English class. Can you find the English error in this question? And then there might be more than one. I'm a math teacher, right? Your job is to see if you can come up with that number.
So, like you use your LN button to log in with your LN.
So every calculator has a log and an LN button. So try it, see if you get those values. So tomorrow's class, we are going to do the actual 5.8 questions. I'm going to hand out your last take-home quiz. Some of it you can do already, some of it is stuff like the first couple questions are things that we're going to do in class tomorrow.